Okay, welcome back. So hopefully you all were able to accomplish the simple conversion practice and feel pretty comfortable with those simple conversions. So the first thing I want to talk about is when we have units raised to a power. We know the relationship already from our simple conversion practice that 2.54 centimeters is 1 inch. Now the question is, what if we want to know how many cubic centimeters are in 1 cubic inch? Well, the trick for that is we just cube everything. We cube inches, we cube one, we cube centimeters, and we cube 2.54. And so what we find is that we have 16.387 cubic centimeters in 1 cubic inch. The way to solve these easily is the same way we've been solving. We're going to take our given unit. We're going to look at the relationship before we cube anything. So if we were converting from inches to centimeter, or excuse me, from cubic inches to cubic centimeters, we would simply look at the relationship between inches and centimeters and then cube everything. Multiply what's on the numerator, divide what's on the denominator, and get our new units and our new value. So let's try one. How many cubic centimeters are in 3.3 cubic meters? So before we worry about the cubic, we just want to know this relationship here, centimeters to meters. So let's take a look at our conversion guide and remind ourselves that there is 100 centimeters in 1 meter. That's the piece of information that we're going to need to know for our plan. Let's make it. So we want to go from meters cubed to centimeters cubed. And for now, ignoring the cubes, we're just going to remember that in 1 meter, there's 100 centimeters. So let's set it up, do our math. So start with what we know, which is 3.3 cubic meters. We would like meters to go away and centimeters to come out. We're going to cube everything. But what's this relationship? In 1 meter, there's 100 centimeters. So now let's propagate this cube. When we cube everything, 100 cubed, and check your calculator, is 1,000,000 10 to the 6 cubic centimeters. Is 1 cubed is 1 over 1 meter cubed. So that's how we would propagate it. And now we take 3.3 times 1,000,000, and we get 3.3 times 10 to the 6 cubic meters. Cancel with cubic meters. Cubic centimeters comes out. So we use those base relationships, and then we let our calculator do all of the cubing that we need. When we're done with that, setting up the conversion factor, we do the same arithmetic that we always do, multiply what's in the numerator or divide what's in the denominator. Let's try another one. How many square inches are in a standard American 167 square meter home? So if we looked at the relationship between meters and feet, excuse me, I lost my train of thought there. We have a relationship between meters and feet here. 1 meter is 3.281 feet. And I think we know the relationship between inches and feet. So let's go from there. So our plan is going to be to go from meters squared to feet squared to inches squared. And now again, ignoring the squares for now, the relationship between meter and feet, meter is about 1 yard and there's 3 feet in a yard. So the relationship here is that there's 3.281 feet in every 1 meter, and in every 1 foot, there's 12 inches. So those are our relationships. So let's set up the conversion factor, starting with what we know, which is 167 meters squared. There is, in every 1 meter, 3.281 feet. and we're going to square all of that in a minute, times, we want feet to go away. We really care about square inches. We know that there's 12 inches in 1 foot. We're going to square all that as well. So let's propagate the squaring now. So 3.281 squared is 10.76 feet squared is 1 squared meter squared. And then, of course, when we propagate the squared in our second conversion factor, 12 squared is 144 inches squared in 1 squared feet squared. 1 squared, of course, is 1. So we take 167, multiply by 10.76, and multiply by 144. You'll see meters squared cancel and feet squared cancel, leaving only inches squared. We see the answer is, with 3 significant figures, 2.63 times 10 to the 4th, or 26,300 square inches in a 167 square meter home. So again, we set up our conversion factor plan with the base relationships. Then we square or cube, depending on what's required of us, all of the values, and then we complete the arithmetic in the exact same way that we've been doing. So I want to introduce one more thing, which is the pass-through conversion factor, which is used to change the dimension of the unit. Now, if you Google pass-through conversion factor, you probably won't find much because it's a term that I've kind of come up with. But the idea is there's some conversion factors which are distinct in which they change the metric of the unit from one to another. And often when we're given questions, the nature of the unit does not just scale, but physically changes. We often look for a pass-through conversion factor to make that happen. So here we have Calvin saying you step in this chamber, set the appropriate dials, it turns you into whatever you want to be. And that's like density. If you have mass and you want volume, you can use density, or if you have volume and you want mass. The density of aluminum is 2.70 grams for every milliliter. So if you have 1 milliliter of pure aluminum, it's 2.7 grams. And if you have 2.70 grams of pure aluminum, it's going to be 1 milliliter in volume. So that relationship allows us to go from mass to volume. Sometimes we take moles of species and dissolve them in solution to do chemistry with them. And so we have the molarity of a solution, which is moles per volume in liters. And so if we want to know how many moles we have in 1 liter of 1 molar, 1 mole per liter solution, we could use that molarity to change from moles to liters or liters to moles. And then finally, as mentioned when we were discussing in the first video, the units, we don't have a SI volume unit, we have cubic volume, but we often use liters in our measuring. And so this relationship is very handy, the cubic length to volume relationships. These conversion factors are ones that are worth knowing. There's 1,000 liters in 1 cubic meter. We've already discussed that 1 decameter cubed is 1 liter, and 1 centimeter cubed is 1 milliliter. These conversion factors help us go from units of cubic distance to volume in liters, and those can also be very handy pass-through conversion factors. And I just want to again emphasize that these are some of the conversion factors to look out for, because otherwise sometimes we're asked to give a value, a unit, that's completely unrelated to what we're given. And without understanding to look for these pass-through conversion factors, we might be really lost on a question. So let me show you. How many grams of mercury are found in 105 milliliters? Hint, the density of mercury is 13.5 grams per mil. But we're asked for grams and we're given volume, so we're going to need a pass-through unit, and that's going to be density relates grams to volume, mass to volume. And so we're going to make a plan. We're going to go from milliliters to grams using the fact that the density which is our pass-through unit of mercury, is 13.5 grams in every 1 mil. If you have 1 mil of mercury, it's going to weigh 13.5 grams in your hand. And if you have 13.5 grams of mercury in your hand, you have 1 mil of volume of mercury in your hand. But more importantly, you need to rinse your hand off and possibly go to a doctor for mercury exposure. So don't hold mercury in your hand. All right, let's start with what we know, which is 105 milliliters. We want milliliters to go away, and we want grams to come out. So we're going to use our pass-through unit and know that there is 13.5 grams in every 1 milliliter of mercury. And so multiply what's on top, and we end up with using 3 sig figs 1.42 times 10 to the third grams, or 1,420 grams of mercury in 105 mils. It's very heavy for its volume. Let's try another pass-through conversion factor. This one might seem a little tricky, but what I can promise you is that this kind of math is going to be extremely common in upcoming chemistry classes. How many grams of NaCl are in a 50 milliliters of a 2.1 molar NaCl solution? So we're starting here with volume in mils, and we want to go to, well, a lot of things, grams and moles. So we're going to need to go from our volume to our number of moles, and we're going to need to go from our moles to our number of grams. And I'm thinking that possibly along the way, no, I think that'll actually be enough. Let's take a look. But we started out with milliliters, and we're going to need to go to liters. So we need to remember that there's 1,000 milliliters in 1 liter, which can get us to moles and get us to grams. So we're going to have to identify 2 pass-through units that we need, our ability to go from milliliters to liters, then the first pass-through unit of liters to moles, and then our second pass-through unit is how to go from moles to grams. So sometimes these things can hide in the question. So here's our plan. We're going to go from milliliters to liters. We remember that there's 1,000 milliliters in 1 liter. We're going to go from liters to moles. We're going to remember that there is 2.1 moles in every 1 liter of this solution. And we're going to go from moles to grams. And we know that in every 1 mole of NaCl, there is, well, let me take a look. Sodium is 22.99 grams per mole. And chlorine, of course, is 35.45 grams per mole. So our sodium chloride is, 58.44 grams per mole, because matter is always conserved. So whatever we start with, we end with. So if we have 2 building blocks of said masses, when we add them together, we have 1 mole of sodium chloride is 58.44 grams. So there are relationships based on our information, and now we can go. So start with what we know, which is 50 mils of our solution. We need to get to liters so we can use our first pass-through unit. So we want mils to cancel, liters to come out. In every 1 liter, there's 1,000 mils. Then we want liters to cancel, and we care about moles. Chemists always work in moles, and we know for this solution, there's 2.1 moles for every 1 liter. And then using our molar mass, our second pass-through, we know that in every 1 mole of sodium chloride, there's 58.44 grams. And all of these things are ratios of 1. Milliliters cancel with milliliters, liters cancel with liters, and moles cancel with moles. So we're going to take 50 and divide by 1,000, then multiply by 2.1, then multiply by 58.44. and I get, with 3 significant figures, 6.14 grams of sodium chloride. Let's try one more. How many moles of sucrose are in 1.54 kilograms of a 2-molar sucrose solution with a density of 1.253 grams per centimeter cubed? So I'm looking for moles. I have molarity, which is moles per liter, so I want volume. I'm starting with grams, well, kilograms, which I can go to grams. And from there, I can get cubic centimeters, which is volume. And from cubic centimeters, I could go to liters, which can get me to molarity, which is moles, which is what I'm looking for. So I think I have a plan, but let's take a look at our conversion factor sheet here. So again, I'm starting with kilograms of solution. So I'm going to be probably using density at some point to get to volumes. But if I use grams per mil, I'm going to have to know that there is 1,000 grams in 1 kilogram. That's the definition. And so then I can get mils or cubic centimeters. But remember, those are the same thing. Our cubic length to volume tells us that if I know cubic centimeters, it's the same thing as milliliters. And then, of course, if I know milliliters, there's 1,000 milliliters in 1 liter. So I can convert to liters. How many liters of solution I have if I have this many kilograms of solution? That's just going from using the density and some conversion factors. But then if I know how many liters I have of the solution and I know how many moles are in every liter, then I can determine how many moles of sucrose there are. So let's make a plan. We're going to go from kilograms to gram. And from grams to centimeters cubed, and from centimeters cubed to milliliters, and from milliliters to liters, from liters to moles. How are we going to get there? In 1 kilogram, recall there's 1,000 grams. And then our density tells us that there is 1.253 grams in every 1 cubic centimeter. There is, in 1 cubic centimeter, 1 mil. That's our cubic volume to liter volume relationships. In 1 there is 1,000 milliliters in 1 liter. And then according to our problem, in every 1 liter of solution, there is 2 moles based on our 2 molarity solution. So now let's start with what we know. 1.54 kilograms. We want kilograms to go away and grams to come out. And there are 1,000 grams in 1 kilogram. Now we want grams to go away and cubic centimeters to come out. And according to our density, there is 1.253 grams for every 1 cubic centimeter. And then that handy relationship from all of those medical dramas we watch on TV, 50 cc's is really equal to 50 milliliters. So 1 cubic centimeter is 1 milliliter. Our molarity uses a volume of liters, so we can use the prefix systems in the metric unit system to see that there is 1,000 mils in every 1 liter. And then finally, with our 2 molar sucrose solution, there is 2.0 moles of sucrose in every 1 liter of our solution. Kilograms cancel with kilograms, grams with grams, centimeters cubed with centimeters cubed, mils with mils, liters with liters, and leaves only moles to come out. So we take 1.54 times 1,000 divided by 1.253 times 1 divided by 1 divided by 1,000 and times 2, and we get 2.46 moles of sucrose. And so I think that, as you can tell, simple unit conversions can be easy to identify. Things get a little bit more complex when we have multiple pass-through conversion factors. And what's important to do is try to identify when units are changing from, for existence, grams to centimeter cubed or moles to liters. When those massive changes are happening, what pass-through conversion factor should we be calling upon? And how do we need to scale what we're bringing in or taking out of those pass-through conversion factors, such as 1,000 grams in a kilogram or 1,000 mils in a liter? How do we need to scale those so we can pass them through the conversion factor to get some new dimension in our metric? So that's the idea. Before I let you go, I want to point out the inevitability as these problems grow more complex. We're going to need to think at times outside of the box. And one of the largest complaints that I hear from young chemists is that the answers and solving the answers require something more than a formula, which can be frustrating. So let's try one of these hard ones. We're going to get some more practice on some of these critical thinking unit conversion questions, but just be prepared that we're going to have to stretch our brains here a little bit. It's going to require some practice before we feel comfortable for this. We're solving real world problems with unit conversions, and we have to be prepared that, the world might throw us a wrench. So let's take a look at one. A curious student like yourself found two circular holes in the ground, each with a 3-inch radius with unknown depths. But let's imagine we find these two holes, one next to each other. We want to know how deep they might be. So for some reason, we have aluminum and iron. We melt them down, 10 kilograms of each. We pour them down the holes, and they don't fill the entire hole up. We let them cool, and we pull these big chunks of metal out of the ground. Which pull is longer, and by how many centimeters? And I'm going to give you some values. The density of aluminum is 2.70 grams per mil. That's a pass-through unit. The density of iron, another pass-through unit, 7.87 grams per mil. And a couple equations. The area of a circle is pi r squared. And the volume of a cylinder, we're going to picture our holes as cylinders, is the area of the circle times its height. So we're going to have to use our conversion factor guide, make sure it's ready, but let's take a look at this problem a little bit. So we have our bore holes, which are 3 inches in their radius and some unknown depth, here we'll call height. And we have an area of our circle which equals to pi r squared. Now, here's something that I want to note. I have a density in milliliters, and I know that an important pass-through unit is 1 milliliter equals 1 cubic centimeter. So when I'm dealing with volumes and densities, I want my units to agree easily. So inches or squared inches is not going to be as helpful as centimeters or cubic centimeters. So I'm going to convert my inches to centimeters first. And this is part of that problem solving, that we have to look at the data that we're given, think about the conversion factors we have, and start to see how we can connect things. So let's do a simple conversion of saying 3 inches, and there's 2.54 centimeters in every 1 inch. Then we just have a 7.62 centimeter radius hole. And if we plug that in, we can say pi times 7.62 squared equals 182 centimeters squared. That's the area here, 182 centimeters squared. So that times the height in centimeters is the volume of our pole. So our volume of our pole is 182 centimeters squared times the height in centimeters, because those would be centimeters cubed. So our volume will need to be in centimeters cubed to make any sense. So let's make a plan. We have kilograms of metal, and we know that we could go to grams of metal using our prefixes. And if we have grams, we could go to mils, the volume of metal, because grams and volume, mass and volume, are related by density. And from mils, we could go to cubic centimeters. And if we divided our cubic centimeters, our volume, by the area, it would give us our height in centimeters. That's what this equation says here. If we divide our volume by our area in cubic centimeters, in square centimeters, we'll get our height in centimeters. So this will be our plan. We're going to start with what we know, which is 10 kilograms. Let's start with aluminum. And we know that in 1 kilogram, there's 1,000 grams. We know that the density of aluminum is 2.70 grams in every 1 milliliter. And we know that 1 milliliter is 1 cubic centimeter. And so we get 3,704 centimeters cubed. And if that is the volume and we divide by the area, which is 182 centimeters squared, we get 20.4 centimeters of an aluminum pole. So now let's back up. Most of our values are going to stay pretty much the same. The only thing that's changing here is we're going to change from aluminum to iron, which has a different density. So we're going to do 10 kilograms of iron. There's 1,000 grams in 1 kilogram always, but now iron is 7.87 grams in every 1 mil. And 1 mil is still 1 cubic centimeter. So 10 times 1,000, 10,000 grams still, divided by 7.87 grams per mil. And times by 1 divided by 1 is 6.98 centimeters deep in our hole of iron. So clearly, 98 centimeters. So clearly the element that's more dense has more mass per volume. And if we're talking only about starting with the same amount of mass, that means we have less volume. Less volume of the same whole area means less depth. And so we only get about 7 centimeters of a pole out of iron when we get about 20 centimeters of a pole of aluminum. So aluminum is taller and taller by about 13.4 centimeters. So that is how we use cubic and square conversion factors, how we use pass-through conversion factors, and some problem-solving examples of how mixing all these things together can make them even more complicated. So now what I would like everybody to do is, after this video, they feel comfortable to start the complex conversion practice assignment. And when you have completed that, we can complete the module with doing a final assessment, making sure we know how to do unit conversions so we're prepared for our upcoming chemistry class. Thank you so much all for your attention, and I wish you luck in the upcoming term.